Hello, and welcome to Lecture 2 of Multi-Loop Circuits in Phys 1204. We've seen the basics of how capacitors and inductors behave in circuits. Now we're going to look at them in slightly more complicated circuits. We've spent a fair bit of time on resistor-only circuits, simple ones, and last video lecture, more complicated ones like this or this. And we've also seen the simplest RC circuits, circuits with resistors and capacitors. So for example, here we know that if the switch has been in position A for a while, the capacitor is charged, and when we flick it to B, there is a current that is an exponential decay with a time constant we know how to find. And similarly, we've seen something for LR circuits which is very similar, that when the switch here has been in position A, there is a current through the inductor, and when we flick it to B, then that current again decays exponentially with a time constant that we know how to find. But what about more complicated mixed circuits? Things like this, or even this, with all three of resistors, capacitors, and inductors. Well, in general, for these circuits, it's hard to find the current as a function of time. But there are two times when it's easy to find all the currents. One is just after a switch has changed state. So for example, in this circuit, just after we close this switch or just after we open this switch. And the other time when it's easy to find all the currents is when a switch has been open or closed for a very long time. So the general problem of finding the current as a function of time is beyond this course, and you may see it in a more advanced circuits course. In this video lecture, we're going to focus on this easier problem. So while we're going to be looking at more complicated circuits, I'll develop the ideas using simple circuits like this, and then we'll apply them to the more complicated circuits. So let's think about a capacitor just after we move a switch. So this switch has been at A for some time, and we know that there will be some amount of charge on the plates of the capacitor. And let's think about what happens when we move the switch to B. Well, we're going to focus on the situation just after. The capacitor is now discharging, so current is running this way. And that current is a rate at which charge is being transferred from one place to another. But that's a finite rate. It takes some time for the charge on the plates to change, and just after we've moved the switch, no time has yet elapsed for charge to change. And so the charge on the plates must be exactly the same as it was just before we moved the switch. Similarly, we know that the charge is proportional to the potential difference between the plates. And so the potential difference across the capacitor is also exactly what it was just before we moved the switch. Now all of those same arguments will apply to when we move the switch back to A. Whatever the charge was and whatever the potential difference across the capacitor was just before we moved the switch back to A, it'll be the same just after we move it back to A. Now let's think about a capacitor a long time after we've moved a switch. So suppose the switch is in position A. Something that's valid for all times is that we can do a loop law. And so here is the loop law around the loop that I've indicated. Now, if the capacitor is not yet fully charged, then Q is increasing. And because epsilon has to stay constant, that means the potential difference across this resistor must be decreasing. Well, eventually the current must decrease to 0, at which point the charge stops changing. We'll be in electrostatic equilibrium. Now again, all the same arguments apply to the situation where the switch is in position B. For all times, we can write a loop law. This time it'll look like this. Now we know that the charge on these plates must be decreasing, and so the potential difference across the resistor must be decreasing. Again, that means the current is decreasing, and eventually it will be 0 once again. In this case, that tells us that the final charge on the plates will be 0. That's different from the case when the switch was in position A. The common feature is that the current ends up being 0 eventually. So, to summarize the situation for capacitors, just after you move a switch, either way, the charge on the capacitor must be the same as it was just before you moved the switch. And that also tells you the potential difference across the capacitor will be the same as it was just before you moved the switch. A long time later, the current will be 0 in any branch containing a capacitor. Here's a caveat. That is not necessarily true if there's an inductor in the same branch as the capacitor, but otherwise it will be true. And the remaining thing to realize is what we mean by a long time, and we've sort of already seen the answer. It's going to be long compared with some time constant, which is related to the resistance and the capacitance, although here for a complicated circuit this would be a total equivalent resistance and total equivalent capacitance for the circuit. So let's work an example. Here is a circuit which has 2 capacitors and 2 batteries and a bunch of resistors and a switch, and I'm telling you that initially the switch is open. There's no charge initially on this capacitor that I've labeled capacitor alpha, although there will be some charge on this capacitor beta, and the switch has been open for a long time. And let's find the charges and currents before we close the switch, so the charges on the capacitors, the currents through the resistors, the charges and the currents just after we close the switch, and the charges and currents a long time after. Now I will say I'm not going to find all of the charges and currents. That would take too long, but once you've found 1 or 2, it's generally easy to find the rest because you can substitute the 1 or 2 into equations that you already have and solve for the others quickly. Let's start with before we close the switch, where note that the switch has been open for a long time. And since that switch is open, that means we can ignore this whole branch of the circuit with the switch in it. So I'm going to redraw the circuit without that branch so that we're not distracted by it. So here I have redrawn the circuit with the switch branch removed, and now I'm, before proceeding, going to indicate which way I think the various currents are. Note that IB has to be the same as I1. And now I'm going to write some loop and junction laws. I'm going to write this loop, which I'll call A, and I'm going to write this loop, which I'm going to call B, and I'm going to do this junction, which I'll call gamma. And note, that normally wouldn't be enough to solve, but there are several things that I know. And the key thing I know is that since the switch has been open for a long time, there is no current through any capacitor. And so I beta is 0. And so I3 is equal to I1, at which point I might as well just call it I. You see what that means is that current is just running around this outside loop, and that's it. And so I can solve for currents out of A. And I can now solve for the charge on the capacitor out of B, because note that with that current and that resistance, I can say that delta V3 is 1 volt. You can check that for yourself. And so Q beta is just. Note that now I know that I3 and IB and I1 and IA, if I wanted to call it that, are all the same. I know I beta is 0, and I know that charge. So in fact, I have now solved for everything. So now let's look at the situation just after I close the switch. So I've written the things we solved for before here, and I've written down the loop and junction laws that I wrote down before because they still apply. And let's think about what's going to happen. So first of all, we know that the charge on capacitor beta will be exactly the same as it was just before we closed the switch. And that means the potential difference across it will be the same. And so in fact, that means the potential difference across R3 is unchanged. And so I3 will be unchanged. So right away, I can just write down that I3 is exactly what it was before, because it's in parallel with a capacitor and the charge on the capacitor won't have changed. So what I would like to find, I guess, is the current through resistor 2. I know the charge on capacitor alpha was 0 before I closed the switch, and so it's 0 just after. And so let me write a new loop law. I will write the loop law for this loop, which I'll call C. Where in writing that I have assumed that I2 is this way. And I know that immediately after closing the switch, Q alpha is 0. And so that's 0. And that immediately allows me to solve for I2. I could now go on to do something like junction delta. And since I now know I2, and I can easily see that since I3 hasn't changed, neither has I1. So I know I3, and I know I1, and I know I2. And so I could use that junction to get the current through this battery, and I could then work through other junctions and find all the currents. So I've summarized the results from just after closing the switch with a ... showing that I have a strategy for the rest. Just working through a bunch of junctions will get me all the rest of the currents. And now let's look at a long time after. So a long time after we close this switch, we now know there's no current through either capacitor. And that means we're back to current only running around this outside loop. And so loop A tells us that we're back to I1 and I3 being the same, and they're 0.05 amps. So in fact, they don't appear to have changed at all throughout all of this. Now, I'll caution you, in between when we closed the switch and much later, we can expect that I1 and I3 probably did change. However, they've ended up returning to what they were originally. Now, the remaining thing I could find, I suppose, I know I2 is 0, and so I could find the charge on capacitor alpha. And that's going to be relatively easy, because I now know that I2 is 0, and so I'm not going to bother to solve it, but you can see that I can now solve for Q alpha out of loop C. Let's see how you're doing with understanding this. So here's what looks like a rather complicated circuit, but it's actually going to be pretty easy to figure out the answer to this. So the switch down here is initially open, and the charge on the capacitor is initially 0. And at some point we close the switch, and I simply want to know just after we close the switch, what is the current through this resistor R2?